All right, let's get going. Welcome, everyone, and thank you so much for joining us on this webinar on quantum optimization with QuEra. Let me introduce myself. I am Alex Kiesling, the CEO of QuEra Computing. I will be your host for the day. And with us, we also have Alexei Belinsky, a senior scientist who has been in charge of getting our first machine, Aquila, up and running and now into your hands. This is a webinar, so all microphones are muted. But we do want to encourage you all to ask as many questions as you have on the Q&A throughout the whole webinar. And we have a fantastic set of people with us who will be answering questions in real time, but we'll also leave some time at the end to answer those questions. Our agenda for today is the following. I'll give you a little introduction to QuEra, our company, and Aquila, our first machine. And then I will pass on the word to Alexei, who will tell you so much more about how to use the neutral atom platform to do optimization. And he will even show you a live demo of one example of optimizing on our quantum machines. At the end, we'll have a Q&A session where we'll get to answer many more of your questions. Let's start with this introduction. So we are QuEra, a Boston-based startup that is coming out of many years of work by some of the leading voices in quantum science and technology at both Harvard and MIT, including the names you see on screen, that have been leading really the efforts in building large controlled quantum systems. And this is the foundation for what we are doing now at QuEra, taking all of this R&D work that has been done over many years and putting it into your hands. At QuEra, we are working towards a future of large, full-scale universal quantum computers. And we are doing so in a way that allows us to provide value at every step along the way, starting today with NIST devices and enabling tools for early quantum error correction work in the medium term. In order to deliver this utility at all steps along the way, we're working on developing some of the most powerful hardware out there today, and you'll hear much more about Aquila. But we are also building software and algorithms to help customers achieve the best value that is possible with the existing quantum hardware, and to allow us to continuously improve on that performance. The technology that we are using and continuing to develop at QuEra has a rich history of development, and particularly of very fast progress over the last several years, particularly by work at universities done here in the area with Harvard and MIT. Here are a few of the scientific breakthroughs that form the backbone of the technology that we use today with neutral atoms. In 2017, the demonstration of control over 51 qubits, but later on expanding that very quickly to hundreds of neutral atoms as qubits that have been used now for a few different key applications in analog Hamiltonian simulation, which we have much more to say, and we had a separate webinar on this recently, but particularly the demonstration of a new state of matter that has been sought after for over 50 years. Also recently, and this is the topic of our chat today, using quantum machines for optimization problems in combinatorial optimization. We are now at the point where you can start doing all of these things on your own, thanks to the launch of Aquila on the Braket service. And we are building up to new tools and capabilities in the near term that are going to open up the possibility to work with much more complex problems, including gate-based quantum computing. Now, let me tell you a little bit about Aquila, which is the machine that is now available to you on the cloud. Aquila works with up to 256 neutral atom qubits in an architecture that we call a field programmable qubit array, FPQA, which you'll hear more about from Alexei. But this architecture allows you to program the interaction of the qubits by their geometry and their connectivity, which is a very powerful starting point to leverage the quantum resources available. It works in an analog operation mode, and this is something that I'll tell you a little bit more about, but it's a key feature of this machine. The way it's built is in a modular way that allows us to extend its capabilities over time by adding new modules that enable new tools. So what do I mean when I talk about Aquila being an analog FPQA? Well, the neutral atom platform, Aquila included, is able to support two different forms of operation: a digital gate-based quantum computing and also an analog one. There's a few pros and cons for each. Of course, digital, the gate-based quantum computing is the most prevalent model for existing machines out there due to its ability to encode arbitrary problems. However, the control and the compounding of gate errors have limited the applicability. The way in which we're operating Aquila for now is in an analog way that, while it takes away some of the universal encoding, it allows us to encode a subset of problems much more efficiently and in a way that throughout the quantum algorithm that is no longer broken into 1 and 2 qubit gates that add a lot of overhead, it makes it much more robust to errors propagating. There are several different applications for which you can use an analog quantum machine like ours. One of them is in solving problems that are quantum by nature, Hamiltonian simulation of atomic twins. There's more information on our recorded webinar from last week on this. Optimization, which we'll be talking about, and there's many others, including machine learning. This is all I have to say, and at this point, I will invite Alexei to join us and tell you all about Aquila and what you can do with it to solve optimization problems. Take it away, Alexei.
Hi, everyone. Thank you, Alex. I hope everybody's ready to peek under the hood of Aquila and find out how it is an analog FPQA, so an analog field programmable qubit array. As Alex mentioned, it's an analog computer, and the FPQA part has to do with how the qubits can be configured from one computation to the other by the user. So the qubits in Aquila are individual atoms that connect to each other based on their spatial arrangement in physical space. And the unique capability that Aquila offers its users is to position atoms almost arbitrarily in a way that allows the user to configure the connectivity of these qubits and therefore redefine the architecture of this quantum processor for the problem at hand. The reason we chose this acronym is to draw the analogy with FPGAs in classical computers. So those are field programmable gate arrays. And for those who are familiar with those, they can be very powerful for solving a specific problem in an optimized way by letting the user configure the components on the classical computer in a way that is optimized for the problem. In a similar way, in Aquila, you have the opportunity to define the connectivity of this quantum processor in a way that might work optimally for your problem at hand. And there are many interesting problems that I will cover today that have geometric character that encode naturally onto positions of our qubits in a two-dimensional space. And so hopefully by leveraging this programmability of the architecture of the processor itself, we can enable early quantum advantage for real-world applications that might be too difficult to implement on a more scalable or more universal quantum computer. Let's go to the analog part. So now that we have defined the architecture the processor, which can be rebuilt every quantum computation into a new geometry. There's also an input component, which is basically an analog waveform that is applied to all qubits simultaneously. While it is different from the situation where individual qubits have pulses applied to them, there's a significant number of degrees of freedom that you can leverage in an analog waveform. And in this case, there are three parameters that parameterize this waveform: amplitude, phase, and frequency. While the level of control is a little bit different from controlling individual atoms, there are some advantages to having to control only a single coherent channel and doing single-step entanglement over the entire processor, as opposed to having deep circuits which compound errors through time, through the quantum evolution. These analog waveforms that you apply globally to all of the qubits simultaneously can be in the form of pulses, if you want, phase slips, phase jumps, or ramps of the analog parameters, such as the frequency and the amplitude. Now that we have looked into how this analog FPQA works as a system, let's go even deeper and look at the building blocks. So in order to build a neutral atom quantum computer like Aquila, you need three building blocks. The first two are the atom itself, which is the physical host of the logical qubit, and an optical tweezer, which is the way that we can grab atoms that live in vacuum and position them relative to each other according to the user's specifications. And the pictures I was showing you in the previous slide were actually fluorescence images of individual atoms in optical tweezers. And this is an example of just one such atom in an optical tweezer as we see it on the camera. Now, how is an atom a qubit? Well, in the case of Aquila, we are actually encoding the quantum information into the ground state and a highly excited electronic state known as the Rydberg state of the atom. And these Rydberg states are special. When driven by a laser beam, and when the electron gets excited to a very highly extended atomic orbital that enables entanglement between the qubits. And let me go through how that is orchestrated. Another atom in an optical tweezer in the same system is another qubit, and for all intents and purposes, they don't see each other and don't talk to each other when they're far enough away. So that means that they can simultaneously be excited to the Rydberg state when they're driven by the same global laser field, which is our analog control. However, when they're brought in sufficiently close vicinity with each other, the interaction between these two atoms in the vicinity, due to these large Rydberg orbitals, prevent both atoms from being excited into the Rydberg state at the same time. And this leads to an effect called blockade. This blockade effect is going to be the key ingredient behind encoding various combinatorial optimization problems onto our FPQA. And it can be a very powerful way to keep your system robust from technical control errors. Now that we got a sense about how the physics of this FPQA works, let us talk about one of our favorite problems in the realm of optimization, known as the maximum independent set problem. It is a problem on the graph, and the problem statement is to find the largest subset of vertices such that none of the vertices share an edge. And so for this simple graph that I'm showing you here, the red nodes that are highlighted in red form basically the maximum independent set on this simple graph. And here's another solution. And as you can see, in many cases, the solutions can be degenerate, meaning that there are many possible solutions that satisfy the maximum independent set problem statement. The graph that I'm showing you here is special. It is a planar graph. and the edges are formed between the nodes in this graph based on a criterion that the edge exists between nodes that are within a unit disk radius of each other. And so this particular instance class, this particular class of graphs is called unit disk graphs. And unit disk graphs are naturally encoded onto the Rydberg, onto our FPQA without extra qubit encoding overhead, which means that each vertex in the graph corresponds to a single atom in our FPQA. Let me just show you how that is done for this very simple graph. We basically position the atoms in their tweezers in such a way that those atoms that are within a blockade radius of each other form an edge in the logical graph that they represent. And so this is a very simple and very, very nice way of encoding geometric graph problems, because there's actually also direct visual correspondence between the two. The reason that we like the maximum independent set problem there are several reasons. One of them is that it's actually an example of NP-hard problems that can be quite general in terms of making statements about solutions to large classes of problems in computer science. In addition, there's recent work from QuEra and our collaborators at Harvard that showed that there is a scaling advantage to the performance of the neutral atom processor relative to a standard classical benchmark. And for us, this means that this is a promising area to look for quantum advantage for real problems over classical processors. I should say that there is a number of sibling problems to the maximum independent set that can be encoded on the neutral atom processor. And I'm just going to mention a few of them. The maximum clique problem, which is basically largest set of nodes in the graph that all have connections to each other. The minimum vertex cover problem, which is basically the set of nodes complementary to the maximum independent set, and the minimum dominating set. And so here I'm actually showing you the minimum vertex cover on that same graph, which is just obtained by obtaining first the MIS and then taking the complementary nodes. Now with this idea about encoding various combinatorial optimization problems and of the kind of the maximum independent set onto our FPQA, I'd like to point to some interesting use cases for these problems. The maximum independent set itself is a great way to solve problems in antenna placement, collision avoidance for self-driving vehicles, and fleet optimization. The minimum dominating set problem can be applied to network optimization in 5G and ad hoc routing. The maximum clique problem is one that can be applied to financial portfolio optimization, either to detect industry sectors in a portfolio of stocks by looking for correlated stocks, or the opposite, finding anti-correlated stocks to make a maximally hedged portfolio. Finally, the minimum vertex cover is something that can be applied as a strategy to immunizing a population or a social network to minimize pandemic spread. If you immunize every node in the minimum vertex cover, the remaining nodes form a maximum independent set and cannot spread the disease through the network. I started by saying that unit disk graphs in a plane naturally get mapped onto our FPQA, and that is indeed the class of problems that has the lowest encoding overhead. However, there are ways to encode general graphs and more general optimization problems onto our FPQA, and that includes hypergraphs such as the 3-SAT problem, general graphs, quadratic unconstrained binary optimization problems, and general graph coloring. And so let me give you a taste of how they can be done for general graphs. For example, let's take this general graph, one of the smallest ones that is a non-planar graph. You can see the edges in this graph intersect, and it is not possible to draw a unit disk radius that would result in these edges for this graph. However, this graph can be mapped onto a bigger graph where each node becomes actually a chain of nodes connected by edges and connected by these what we call gadgets that implement crossings between the edges. And this bigger graph can then is a planar graph and is a unit disk graph that can be solved for the MIS on our FPQA. And the encoding overhead in terms of the number of qubits from this general graph to one that can be encoded onto the FPQA, in the worst case, is a quadratic overhead, meaning that you need to square the number of atoms as you have nodes in the initial graph. While this can be prohibitive initially for encoding large useful problems, it is a good start. And with our plans to offer much larger FPQAs in terms of numbers of qubits, more and more generalized problems should become accessible. If you're interested in doing these mappings from general graphs that your problems might map onto into this FPQAs, there's code that we have made available through our open source repository called Unit Disk Mapping. Please feel free to check out that code at the link below. Now that we've talked about this field programmable nature of our processor and how to encode optimization problems, let's talk about the analog computing part. And this is where we will bring in the Hamiltonian, which is an object that physicists use to describe in detail the dynamical behavior of a quantum system. And you can think of it as a cost function, energy cost function for the purposes of our optimization problems. There are three components to this cost function. The first component on the left encodes the interaction between the qubits, or the energy you pay, the energy cost you pay when the qubits are too close to each other, and you as a user get to control that term via the coordinates of the atoms in the plane. The second term has to do with the laser drive, or this global excitation of the atoms into the Rydberg state, and that is this analog program that you input into the FPQA, and that is programmed by time domain dependence of the strength of the laser drive and the phase of that drive. And then finally, the last term that you see in red is the detuning of the global drive from the ground to Rydberg resonance, and this term can be thought of as an energy bias that gives preference for atoms being in the ground state or in the Rydberg state. And so I've shown you Hamiltonian, which can be daunting for some, but I would like to emphasize the following point. This is as close as you can get as a user to programming a quantum computer as close to the hardware as possible. And we hope that this access to direct access to the physics of the underlying quantum system can be leveraged by our users to uncover advantage of this quantum system over classical compute resources available today. Let us talk about one particular analog compute schedule that you might apply in our system. And we call this the adiabatic state preparation. The idea is the following. When you can encode the MIS, for example, into the ground state of this Hamiltonian, and the ground state can be a trivial one, where all the atoms are basically in the ground state when this energy bias term is large negative. But when you slowly sweep this term, when you slowly sweep this detuning parameter, from large negative to large positive, the system prefers to be in an excited state, subject to the constraint that atoms within a blockade radius of each other cannot all be in the Rydberg state. And so as you sweep slowly from large negative to large positive, the system goes from the trivial ground state to this non-trivial many-body state, which encodes the MIS solution in which atoms are in the Rydberg state at the end of the computation. And this adiabatic state preparation is the protocol that I will walk you through when we do the demo through the Braket service. I will emphasize before moving forward that adiabatic protocol is just one of the possible analog schedules that you could apply, or analog algorithms that you could apply. There are many more that our system could handle, and just to mention a few: quench dynamics, a variety of variational quantum algorithms, the quantum adiabatic optimization, quantum approximate optimization algorithm, and quantum sampling, among many others. Now that we have gone through the mechanics of Aquila and ways that you can encode optimization problems, we would love you to go and play and try to find problems that are useful, but also can bring advantage to you as a user from the quantum machine that we are offering you. The areas where you might find advantage are as follows: classical problems where there's benefit to getting solutions faster or at a higher quality level. For example, approximate solutions that are closer to the true answer is one promising area. Problems that are really hard classically to the point that nobody's attempting them because they are so daunting for the classical computer, potentially by enabling them to be solved at all on a quantum computer or our analog FPQA, this can open up many application areas that weren't even conceived of before. Just a few that we would like to point out where we expect to see advantage earlier than anywhere else are optimization. This is the topic of this seminar. So in particular, problems which have a strongly connected character or which have many constraints. Generative modeling is an area where you might benefit from sampling from non-classical probability distributions, and that could potentially be done in a very powerful way by sampling from quantum many-body distributions. And finally, simulation of problems that where the original problem has strong quantum effects, and that is actually the topic of the webinar that we had last Monday. If you would like to review that, please look at the recording of that webinar. And finally, as I hope I made clear in this presentation so far, problems with the geometric structure would be the first place to look, because they can get encoded onto our FPQA with very low qubit encoding overhead. All right, so without further ado, I would like to move on to the demo of Aquila. And I will go to the Braket interface and submit jobs to Aquila with you together through that interface. But first, let me walk through the basic steps that we're going to cover there. We will first try to encode a graph that we have chosen into the atomic coordinates to create the atom register for Aquila to arrange. The second step will be to specify this analog compute schedule, by specifying time series for the strength of the drive, the detuning, and the phase of the global drive applied to the atom register that we make. And then finally, we'll retrieve the results and process the data, visualize it, get statistics on it. And I hope the sky's the limit for what you can do with the data on your own time later. Here we go. Let's go to the product demo. What you see here is my browser, where I'm logged into my AWS account. in particular, I'm in the Amazon Braket service. Braket is a service that AWS offers that enables users of AWS to access quantum hardware of different kinds from different providers and integrate the use of that hardware with whatever other resources from AWS the users are interested in leveraging. That includes storage and various classical compute resources, cloud application development, and so on. Here is the panel of the service that shows you all of the different hardware providers that you could send your jobs to, and this includes trapped ions, superconducting qubits, photons, and over here you see Aquila from QuEra, which is the first neutral atom quantum computer on the Braket service, and indeed the first neutral atom quantum computer available via a cloud service anywhere in the world for the public. If you click on Aquila, you will go to a page that has a short description of the device, the cost of running it, when it's available next, its current status, and over here below, the constraints that you need to be aware of when creating and submitting programs to Aquila. If you look at the tabs on the left, you can go to notebooks, and this is where the Jupyter notebooks that you've spun up will be located. And I'm just going to go straight to the one that we prepared for this demo. So this is a Jupyter notebook. It is a self-contained notebook that also walks you through some of the physics and the best practices for how to encode optimization problems onto our FPQA. And I'm just going to walk through this notebook with you step by step and point out some of the important lines in this code and execute this notebook with you. We'll first do a couple of basic imports and start by getting a sign of life from Aquila. So for that, we need to first import the AWS device, which is an object that contains information about all of the hardware, contains handles to all of the different quantum hardware on the Braket service. And then we're going to get a handle to Aquila via this identifier, via this ARN, which stands for Amazon Resource Number, and assign this handle to this object called QPU. And I will reuse this object later on in Notebook to submit jobs to Aquila to pull capabilities of it and to get results. So let us start by actually querying what Aquila is capable of. So I'm going to execute qpu.properties.paradigm, and then display the dictionary that comes back to me, which actually contains all of the constraints and capabilities that you should be aware of. And in particular over here, I pulled out the C6 coefficient, which is that parameter, that constant that is in front of the Hamiltonian term that controls the interaction between the qubits. We will use this C6 in creating our program for Aquila. Okay, now that we started to talk with Aquila, let us go back and think about optimization problems. Here is an introduction that I already went through in the slides, that is also in the notebook, that walks you through how the unit disk graphs are mapped onto atomic registers with a Rydberg blockade radius that stands for the unit disk graph. And what we will do here is we will start with a very simple graph that is of the type called King's graph. It's basically a graph where the nodes live on a grid and have neighbor and next neighbor connections. Here is our simple example graph. That is a logical graph, and we now need to turn it into an atomic register. As you might imagine, a number of unit disk radii would satisfy this graph, meaning that for a number of unit disk radii, you would get the same logical graph. And this range can be seen here. So for example, if we focus on the node that's shown in red, the minimum unit disk radius that satisfies the graph is the dotted one, and then the largest unit disk radius is the solid line. And what we're going to do is we're going to pick something in the middle, the geometric mean of the two, to make the encoding maximally robust when we go to the atomic system. And so we will take this dashed radius as the unit disk radius, and now we will create the atomic register by scaling the blockade, by scaling the physical coordinates in which the atoms will be located, will be placed by the ratio of the blockade radius and this unit disk radius in the logical graph. So this is the next step. We compute the blockade radius from the C6 coefficient that we figured out from the Aquila capabilities, and the final detuning that we will use in the adiabatic protocol. This is the ratio of these to the power of 1/6 is indeed what sets the blockade radius. So we'll take the blockade radius and we're going to find out the scaling factor from the logical graph to the physical graph by taking the ratio of the blockade radius and the unit disk radius. So here we go, and out comes the atomic register with coordinates in meters. And so you can see that the typical distances between the atoms will be on the order of micrometers here. So we figured out now the coordinates of the atoms that we want to put into the FPQA. And now let us define the adiabatic evolution protocol. Defining the adiabatic protocol is effectively comes down to specifying time series for the drive strength, basically the laser intensity, the phase, and the frequency of the drive. And so here's my time series. There are 4 time points, and then the phase stays constant. The amplitude jumps to a value that stays constant through the coherent evolution, and then the frequency, which is this second graph, gets swept linearly from this large negative value to this large positive value in order to take the ground state of this many-body system from the trivial to the MIS state. After we have defined the atomic register and this adiabatic protocol, we're going to package those two objects, the register and the drive, into this analog Hamiltonian simulation object, which we will submit as a program to either a simulator device on Braket or Aquila. Let us start with the simulator. So the graph, we started with is small enough that a classical simulator can handle it. In fact, it is good practice when you can to first run your program on the classical simulator to make sure everything is as you expect before starting to use this precious quantum resource, which is the Aquila FPQA. So for the small graph, let us execute it on the local simulator, which is basically provided by Braket and can be pulled as follows from this import. And then we take our AHS program, that's the packaging of the register and the analog program, and we execute device.run to run it on the local simulator. So here we go, we've executed on the local simulator, and now we are displaying a sampling of the results from the 1,000 shots that we sent, that we requested. And you see that there are some solutions which are not the maximum independent set, like the first two, and then here's the one on the right is the maximum independent set. We're going to do some classical post-processing of the data in order to remove violations of the independent set constraint, and I will come back to this point when we deal with a bigger graph, but we will be doing the same post-processing in all of the jobs here. And after doing the post-processing, we're going to look at the statistics of the solutions from this local simulator. You can see that this is a distribution of independent set sizes, and most of them fall into the size 3 bucket. And then here's a sampling of the solutions from this largest bucket. You can see that there's mostly the same 3 nodes that come out from the computation as an MIS. All right. Well, let us now do something a bit more interesting. Well, first of all, let's start using Aquila, but let us also take a much bigger graph, which the quantum computer can actually handle. Here we're going to generate, again, a random King's graph. Again, those are nodes that live on the grid and have neighbor and next neighbor edges. And we're going to generate the graph with a density of 70% on a 15 by 15 grid. And we're going to go through the same steps that I showed you on the small graph of scaling the logical graph by the ratio of the blockade radius and the unit disk radius, such that we actually get the atomic coordinates to submit to Aquila. So this is already the atomic coordinates that we will be submitting. We will reuse the same adiabatic protocol that we defined for the small graph, and we are ready to submit the job to Aquila. This is the cell that does it. I have put a safeguard at the top to make sure I don't accidentally submit jobs that are not ready. And I recommend that everybody using the notebook does something like that to make sure that they don't accidentally submit jobs to the QPU until they're ready to do so. But I'm going to comment it out because we are ready to go. As a reminder, we already imported the AWS device and assigned the Aquila ARN to the QPU object, but I'm going to do it here just in case. I'm going to request 1,000 iterations of the quantum computation, 1,000 shots, and then I'm going to execute this QPU.run line to submit the job. Here we go. Off it goes. The job has been submitted into the queue that Braket operates, and we got a task identifier back, which we can use to retrieve the results when they become available. Now, we are not going to wait for the job to go through the queue because we need to move on with our demo. But what I will do is pull results from the same job that we ran on Aquila a couple of days ago in order to move on with our presentation here. So I'm going to pull the results for this job. Here's a sampling from the 1,000 shots that we ran of the results. So the nodes that are red are basically atoms that ended up in the Rydberg state after the adiabatic protocol, and they are supposed to represent the MIS solution. You can see that there's going to be a distribution of actual sizes of the sets of red dots, and you can also see that in some cases there's a violation of the independent set constraint, like in these clusters of 3 Rydberg atoms near each other. And that's because the device does have errors and it is not perfect. And it is important to run the program many times and look at this distribution of solutions. But it is also important to do this classical post-processing that I mentioned before. And here's where I will go into a little bit more detail. You know that these small clusters of connected red dots are not allowed by the MIS, by the independent set constraint. So one way to search for a better answer that also doesn't violate the constraint is to take these small clusters and randomly remove nodes from them until the independent set constraint is satisfied for each of them. And so that's actually what the classical post-processing step does. We're going to apply this classical post-processing and, as before, plot the distribution of independent set sizes and show a couple of samples from the post-processed solutions that have that are in the largest bucket. So the bucket with size 43. So here are 2 of the solutions in that bucket, and here's the distribution. Because we're trying to solve the maximum independent set problem, we're going to be interested in solutions that are in this largest bucket. The true maximum independent set size for this problem is 51. So in this case, we haven't gotten to that answer. The way to try to get closer involves running more iterations, so that just statistically speaking, you have more instances of solutions with larger independent set sizes. And the more you run, the closer you will get to the maximum independent set. Furthermore, the quality of the solution will depend on the details of that analog schedule. And so, because there are so many degrees of freedom you can play with there, there's ways to you can try optimizing the exact ramp waveform to make sure it optimizes the maximum independent set size. We just use the trivial one, but there's a lot more to play with there. And so this is how you would try to solve MIS on Aquila. And I would like to wrap up this demo with a real world example, or a toy example that could be a real world example rather, from our favorite city. So this is going to be locations in Boston, and I would like to emphasize some of the best practices in turning your problems into problems that can be mapped onto Aquila hardware. There are geometric constraints to the way you position those atoms and define their connectivity. The constraints, as I mentioned before, can be pulled out from this from the device. And so here I'm displaying just the geometric ones. You can see that there's a minimum distance between atoms that is allowed. There is a bounding box around the area where you can place the atoms. So you have a limited region where your atoms can sit. There's a position resolution, meaning that you can't rely on atom positions being more precise than about 100 nanometers. And one very important one is that each atom belongs to a row, and the more atoms that share a row, the more atoms you can use in Aquila. That is a nuance of how our hardware arranges atoms in a plane, and so it is important to think of ways of mapping your graph problems onto atomic registers in a way that there are as many rows as possible, or as many atoms share rows as possible. And so what we did here to illustrate this point was to take a map of Boston and Cambridge, the cities that Aquila and QuEra originate in, and we picked locations from that map. We picked a couple of intersections, and we actually tried to make them fit onto rows. And this is a graph with 130 nodes from intersections in Boston and Cambridge. These locations were handpicked, but one way you can think of this problem maybe having some real world applications is imagine that those are locations for possible antenna upgrades for a 5G network, for example. And the new antenna have a bigger range, and they must not interfere. And so the problem becomes picking the nodes that you want to upgrade to provide maximum coverage, but minimizing interference, meaning that the nodes that will get the upgrade should not be adjacent nodes. They should really form a maximum independent set. So we're going to take this graph, and we're going to again scale it by the blockade radius in order to get the atomic register, and then we're going to submit the job to Aquila with 1,000 shots using the same adiabatic schedule that we defined in the beginning. Off it goes. Here's our task ID returned to us, which you can use to pull the results. And again, I will not wait for the job to go through the queue, but get the results from the same job we submitted a couple of days earlier. here are samples from the 1,000 shots of the possible antenna locations. We will do this classical post-processing in order to remove independent set violations. And ta-da, here's the distribution. And here's one of the solutions that fall in the largest independent set size bucket. Again, this is not the maximum independent set, and one can get a lot closer by running more iterations and by optimizing the adiabatic protocol and maybe thinking of more clever post-processing steps for the data that you get from Aquila. So with that, I'd like to turn it over back to Alex for closing remarks and for Q&A.
Thank you so much, Alexei. And thank you for showing us how to encode all of these different problems using the Braket interface. Before going into the Q&A, I just want to tell people a little bit about what they have to look forward to in terms of what they'll be able to do with our products. Currently, Aquila is, exactly as you heard from Alexei, a very powerful tool for exploring optimization problems. There's also there's a recording of a simulation, quantum simulation webinar out there. But Aquila, as we've mentioned before, is built in a modular way that allows us to add more capabilities on top of it. And these capabilities will enable you to extend the types of problems that you can solve, for example, by introducing more controlled local detuning, but also to move towards a gate-based architecture by having the ability to control and program individual and 2-qubit gates. There's much more to it, and there's a very exciting future in terms of technological development at the company. A lot to look forward to. Now we're going to move on to the Q&A. And Alexei, I'm going to start with just saying that there's been a lot of questions, and we're very thankful for everyone for submitting your questions. Our team has been doing everything in their power to keep up with all the questions that have been coming in. But one that I see that would be worth spending a little bit of time on, Alexei, is questions about programming other algorithms. For example, is it possible to program general QUBO problems or weighted graphs using Aquila?
I'm glad that that question came up. Currently, this QUBO problems and weighted graphs aren't possible in Aquila, but we're planning a feature release where the nodes of the graph in your optimization problem could be weighted using a module that we will kind of upgrade Aquila with. And that actually goes to the slide that you just showed, Alex, where there's a number of features that can be added to Aquila while it's in operation. And you basically release these features over time. So we're planning one such upgrade, and I think it will enable even more interesting problems to be run.
Great. And talking about new features, there's a question on whether Aquila can be converted to a gate programmable device. I hope that my last slide answers that. The answer is yes. The neutral atom platform, and particularly what you're seeing here on screen, which is a picture of one of our systems, can function both as an analog and a digital quantum computer. There are some planned future upgrades for Aquila and some of our upcoming systems that will enable it to be programmed as a gate-based quantum computer. Interestingly enough, and just as a sneak peek, this will turn it into a Qtrit control device. Moving on to another question, and this one I think is fascinating. Alexei, how do you verify if the analog quantum computer is doing what you expect?
That's a very good question, and that can be a challenge for any computer in the field. In reality, it's a general problem for the field. As you build a machine that classical computers can't keep up with, how do you know that it's doing the right thing? One approach is to do benchmarking at an ever increasing scale. Start with problems that your classical computer can solve, compare the answers, increase the size, make sure everything remains correct, and then at a certain point, the classical computer cannot keep up. But hopefully you have confidence by that point that your quantum computer is doing the right thing, and then that is where hopefully the usefulness of your quantum computer takes over, meaning that if your quantum computer is providing solutions that are better, then that should speak for itself. Meaning that, for example, if your quantum computer is giving you a more optimal network solution to the classical algorithms you might have been using before, then that is already commercial value, and some users might not care about anything beyond that. As long as it's useful, it is useful. And then finally, I will say that for many problems, such as NP-complete problems, and MIS is one of those, the solution might be very hard to find on a classical computer, but it is easy to verify that it is correct on a classical computer. And so you can continue benchmarking your quantum computer if you have efficient verification, at least for those problems where you have efficient verification.
Great. I see a few questions that are in one way or another asking about differences between Aquila and other quantum hardware, particularly annealing hardware. So what can we say about differences between the two? Well, for one, as you heard Alexei talk about the FPQA nature of this, Aquila allows to reconfigure the connectivity for every time that the task is run. So this is something that is quite unique to the approach that is taken, and it's really thanks to the ability to tear apart and rebuild the way that the atoms are placed relative to one another. This is somewhat unique to our approach. The other thing is in terms of the use cases that have been done. While here we are talking about Aquila as a tool for exploring quantum optimization, there's much more to this platform, and particularly with a very similar system to Aquila, there have been results that have demonstrated things like new quantum phases of matter, like quantum spin liquids, that were achievable thanks to a unique combination of the constraints that is imposed by this Rydberg blockade radius that Alexei introduced, and the ability to preserve the quantum properties of the system throughout the entire evolution of the algorithm. So these are some of the highlights of the neutral atom, that the platform that set it aside from other annealing hardware that you may have heard of. Alexei, there's also some questions about related to mapping other problems and so on. You're giving people access to up to 256 atoms, but if they want to solve problems that are smaller than that, what can they do? Is it possible for them to define where the atoms are placed? Is this done automatically? Do they have to worry about disconnecting to the rest of the 256 atoms? Can you tell us more?
Right. So you can choose the number of atoms and where they are up to 256, which means that you can define a processor which is one big connected 256 qubit array, or you can leverage the flexibility of the platform to create an array of registers that that do not talk to each other, that are smaller, each of them, but that can basically compute your program in parallel. We don't have it in this presentation, but we have some visuals of atoms that are placed in, 28 3x3 registers and so on. And so that is another very powerful feature of the platform, is that you can parallelize, classically parallelize the throughput by leveraging the area and the number of qubits that are available.
That is awesome. Thank you so much. With this, I'm just going to thank you all again so much for joining us on this webinar, and let Pacman walk us out of here. All right, everyone. Thank you very much. Have a good day.